All right, let's talk about arc length and angular versus linear velocity. So first things to review is what an actual radius is. You know that, right? Given any circle, a line connecting the center to any point on the circle, that's a radius, called the arc. Diameter is two of those radii, right? Two radiuses, that's the diameter. By definition, it's a line that crosses through the center it's a line on a circle that crosses through the center, period. The points will always line up. Okay, and then here's the part that you got to pay attention to. Circumference of a circle, right? The perimeter basically around is equal to 2 pi times r, or pi times the diameter, whichever one that you're given. So it's 2 pi r, because if you convert that to degrees, it's in radians, that's 360 degrees. So it's talking about, okay, if I take the full circle around and I multiply it by this radius, that gives me the distance all the way around there. And then this idea of a sector, that's just a slice of a circle. It's like a pizza slice, right? So there's a sector. Okay, basic vocabulary just to review. First topic is arc length. This is, here's a sector, right? Little pizza pie. An arc length is literally the length of the arc produced between the two sides of an angle, right? So here is the angle in a circle. It's called a central angle. And then this is a radius and a radius. Well, this is the arc length right here, this piece right there. And to find it, it's just this easy formula. Arc length, which they call it little s, I don't know why, is just to take the radius and then multiply it by that central angle. Whatever that measurement is, you're going to multiply the radius by it. Just like you did back here with circumference. Circumference is the distance around the whole thing, which would be 360 degrees or 2 pi. So in this example here, it tells us that this length is 8. So my r is going to be 8. Then it also shows us this angle going from there to there, which is 350 degrees. So our angle, our central angle, is 315 degrees. Now this formula, S equals R theta, it doesn't make sense for me to multiply 8 by 350 degrees and have it be the length of this portion of a circle right here, right? That would be like almost 3,000 right there. So what it's talking about in this formula is that you have to have your angle be in radians. This is how most of the mistakes will get made in these problems, is that you forget to convert it to radians. So 315 degrees, remember you multiply it by pi over 180, then take your angle and reduce it down. I'm going to show the in between. And it's going to, let's see, that's quadrants, 7 pi over 4. So that's actually your theta. All right, now let's find our arc length. Arc length S is equal to R, which is 8, times 7 pi over 4. Now if you multiply that out, simplify it, you'll end up with 14 pi. Now arc length is a measurement. So as far as computing it, I mean 14 pi is a perfectly valid answer. But if this were some kind of story problem, right? We wanted to know, here's this circle, we need to know the length of the arc, then you would probably give it in decimal form, which is about 44, whatever the measurement is, centimeters. Okay, this next one says, find the length of an arc length, of a circle with a radius of 21, got our R. and a central angle of 15 degrees. So theta equals 15 degrees. Have to change that. Got to turn it into radians, which is pi over 12, I think. Yeah, pi over 12. So our arc length S equals 21 times pi over 12. Okay, that's 21 pi over 12. 21 and 12 reduced down to 7 pi over 4, which is about 5.5-ish. 5.5 meters. So this was just applying the formula. It's not an actual story problem, so the whole approximate answer might not be that important. But when you get to actually applicable problems, that approximate's going to be important. This one says, how far does the tip of a 14 centimeter long minute hand on a clock move in 10 minutes? So this is an actual application problem now. So picture a clock, right? We got 12, 1, 2, 3, so on. There's 6, there's 9, 10, 11, blah, blah, blah. Okay, and we've got this 14 centimeter long minute hand. So let's pretend like that's the radius. Should have drawn a better picture. Okay, ta-da, my picture improved magically. A 14 centimeter long minute hand. So we're going to pretend like that's the radius of this circle, and it's going to be 14 right there. Then it wants to know how far does the tip move on a clock in 10 minutes. So here's the tip of that guy. How long would 10 minutes be? Well, that would be over here at 2, right? Minute hand, there's 5 minutes, 10 minutes. So how far does the tip move is just asking you to find this arc length right here. All right, arc length is r theta. We have r. That was nice, they gave it to us. But we don't have theta. All we know is that it moves 10 meters on that actual clock. So here's the thinking you got to do. All together in one full circle, there's 360 degrees. I need to know how many degrees are actually in 10 minutes. I'm sorry. That was silly. I don't know why I wrote that. So 360 degrees total. And then we need to divide that up into 10-minute portions. So we got to figure out how many 10-minute portions are there. That sounds weird. There's 5, 10, so there's 1. 15, 20, there's 2. 25, 30, there's 3. 35, 40, there's 4. 45, 50, there's 5. 55, 60, there would be 6. So in a 10-minute block, it goes 60 degrees, right? That angle right there is going to be 60 degrees. Now, if I took the clock off that altogether, and I just said, hey, here's the circle, right, on a coordinate system, and I'm starting up here, and I'm going 2/3 of the way this way. Well, in a regular coordinate system, that's 90 degrees, right? A third of that is 30, so 2/3 would be 60. That's comparing it. I think looking at a clock, it's a little bit easier to do. You can also think about it, the fact that there are 12 numbers on here. So 360 divided by 12, that's 30. So every time the clock moves to a new number, that's 30. And it moves 2 to get to 10 minutes, so that's where the 60 also comes from. All right, so that's our theta. Theta equals 60. Can't leave that though. We've got to convert it to degrees, which is pi over 3. Okay, arc length is equal to 14 times pi over 3. Okay, that's 14 pi over 3, or approximately 14.7 centimeters. Okay, next one says an arc of 60 degrees. That sounds like a theta. Has an arc length of 50 pi. Arc length is S. Then it says, what is the circumference? All right, so let's think about this for a minute. First of all, theta is in degrees, so I'm right away going to change that to radians because I know these calculations have to be done with radians. So it's the same as the last one, theta equals pi over 3. And then it says S equals 50 pi. Well, there's a formula for S that we're learning that says S is the same thing as R times theta. Well, that means that I can form this equation if S equals R times theta, but it also equals 50 pi, but I know what theta is. Don't get lost on this one. All I'm doing is rewriting it with things that I know. So R times pi over 3 equals 50 pi. Now, why did I do that? Well, in order to find the circumference, the formula is 2 pi r. So this problem is trying to get all fancy on you and say, okay, well, you're given an arc length now and an angle. Use that information to find r, and then plug r into your piece over there, into your formula for circumference. So right now it looks like this. R times pi over 3 equals 50 pi. Now to get rid of a fraction next to a number, you multiply by its reciprocal. So I'm actually going to multiply by 3 over pi times 3 over pi. Those will cancel, and I get that r equals 3 times 150, or, sorry, 3 times 50, which is 150 degrees. And then if we turn that into, oh, it's not even degrees, it's just 150. It fooled me because I crossed out the radians, but this is in radians. It's not an angle because everything was in radians. So r is 150. Now I'm going to write radians to remind us of that. If r is 250, then our circumference here, is going to be 2 pi times 150, or 300 pi. And you could do an approximate for that if you wanted to, but it's not really computing an actual measurement, so we'll keep it at 300 pi.